Hello everyone, this is Arije Docas, and now we are going to talk about the models used in this study. So we applied four semi-supervised learning models: the label propagation, self-training XGBoost, transductive support vector machine, and the Laplacian regularized least squares. The main reason for selecting these models is because of the nature of our dataset. About 75% of the data is unlabeled, which makes fully supervised approaches ineffective. So instead, these models allow us to learn from both labeled and unlabeled data, patient data. So we also combined both the graph-based methods and the tree-based methods. The graph-based method models help us capture relationship between the similar patients, while the tree-based models help to capture the complex nonlinear interactions between the biomarkers. So this combination improves both learning performance and robustness. So we move to the label propagation architecture. So this is a graph-based semi-supervised learning model. Here, each patient is represented as a node in a graph, and connections between patients are based on similarity in their clinical features, such as the CD4 count or the blood markers. We compute similarity using a radio basis function kernel, which gives higher insights to more similar patients. So the architecture consists of a similar matrix, a graph structure, and label distributions across nodes. Initially, only a small portion of the nodes have known labels, and the rest are unlabeled. The idea is that similar patients are likely to have similar outcomes, so labels can be propagated through the graph. Next, we look at the XGBoost architecture. So this is a tree-based ensemble model. The architecture consists of multiple decision trees built sequentially, where each new tree learns from the errors of the previous trees. This allows the model to capture complex and nonlinear relationships in the data. What makes it semi-supervised is the addition of a self-training loop. So after the initial training on the labeled data, the model predicts the labels for unlabeled patients, and only high confidence predictions are added back into the training set. So the architecture combines boosting with the iterative pseudo-labeling. Next, we look at the transductive support vector machine model architecture. Now looking at the SVM, this model extends the traditional SVM by incorporating the unlabeled data into training. Instead of just separating the labeled points, it tries to position the decision boundary in regions where there are a few data points. So the architecture includes separating hyperplane labeled samples guiding the classification, and unlabeled samples influencing where the boundary should lie. This helps improve generalization, especially when labeled data is limited. Next, we have the LAP RLS architecture. So finally, the Laplacian regularized least squares. This model combines the regression with the graph-based learning. We construct a similarity graph between patients, then compute a Laplacian matrix that represents the structure of that graph. We also compute a Kernel matrix to capture the feature relationships. The model then solves a regularized optimization problem that ensures predictions are smooth across the graph. So similar patients will have similar predicted outcomes. Next, we go to how the label propagation learns. The model works by iteratively spreading labels across the graph. Each node updates its label based on its neighbors, with more similar neighbors having more influence. So the labeled nodes remain fixed to prevent incorrect updates. This process continues until the labels stabilize. The key hyperparameters include the RBF canal, the number of iterations, and the convergence threshold. Then here the graph structure is very important because it determines how information flows between patients. Then next we have how the XGBoost learning happens in the two stages. So first, it's a standard gradient boosting where the trees are built sequentially to minimize prediction error. Then comes the self-training phase. The model predicts on unlabeled data, and only predictions above a confidence threshold, typically 0.9, are selected. These are treated as pseudo-labels and added to the training data. This process is repeated for several rounds. And here the key hyperparameters include the learning rate, the tree depth, the number of estimators, and the confidence threshold. This approach allows the model to safely expand its training data. Then we have the TSVM learning and optimization. So for TSVM, the learning process is iterative. We start by training a standard SVM on labeled data. Then we assign the pseudo labels to unlabeled samples. The model then updates the decision boundary to maximize the margin while considering both labeled and labeled data. This process repeats until convergence. The key hyperparameters here include the penalty parameter for the labeled data, the penalty for unlabeled data, and the kernel type. The goal is to place the boundary in the low density regions for better separation. Then we have the Laplacian regularized least squares optimization. Learning is done by solving a mathematical optimization problem. The model balances three things: fitting the labeled data correctly, keeping the model simple, and maintaining smoothness across the graph. So unlike the label propagation, this is solved in a single step using the matrix operations. And here the key parameters include the regularization strength, the graph smoothness, weight, the kernel parameters, and number of neighbors in the graph. This ensures stable and consistent predictions across similar patients. Then when we talk about the hyperparameters, across all models, the hyperparameters play a key role in performance. So we tune the parameters such as the kernel type, similarity scales, number of iterations, learning rates, tree depth, and confidence thresholds. These were selected carefully to balance the accuracy and generalization. Improper tuning could lead to overfitting or poor generalization, especially given the limited labeled data. So finally, we applied the explainable AI techniques to audit the models. This is very important because the system is intended for the clinical decision support. For the XGBoost model, we use the feature importance and the sharp values. To understand how each biomarker contributes to the predictions. And for the graph-based, we analyzed how labels propagate and how nodes influence each other. So this helps us ensure that predictions are medically meaningful and not biased. It also improves trust, which is critical in healthcare applications. So in summary, these models work together These models work together to effectively leverage limited labeled data, capture complex relationships, and produce interpretable predictions that can support clinical decision making. Thank you for listening. This is all I had.